Welcome, loyal followers. This is Renee McCormick with the National Math and Science Initiative. This is the second installment of solving equilibrium problems that deal with solubility equilibriums. These are our special Ks that we call KSP, and we're going to work through 3 AP problems that are from a more recent time frame than the first recording. So 1998 is where we shall begin. This one asks us to solve the following problem related to the solubility equilibrium of some metal hydroxides, which are generally insoluble, in aqueous solution. So the solubility of CuOH2, lovingly called copper 2 hydroxide, is, they just told you X. When they tell you solubility, molar solubility, solubility in whatever, they're basically telling you X. The in whatever part of this one is that we have grams per 100 milliliters, which think of as a tenth of a liter to make your math easier a bit, at 25 degrees Celsius. So I put this X in quotes because it's not the real X. We'd have to really go to moles per liter, which, oh look, they ask us to do that in part 2 here anyway. So we'll get to it in just a moment. So the first thing is the pity point. Let's get the pity point out of the way. The pity point is for, I don't know really how to work an equilibrium problem, but I know just enough to be dangerous. So I understand that this is going to be a solid, and it's going to be in equilibrium with its ions. So they ask us to write a balanced chemical equation for the dissociation of copper 2 hydroxide. And they give you the formula, which is awfully nice of them. And so you just put your little double-edged arrows, and you get the proper charges and the proper numbers of each of the ions. And you'll get a point for that. So you're kind of a fool not to write that. All right, sometimes they'll ask for it, sometimes they won't, but they give a point for it pretty much automatically. So even if they don't ask for it, write it somewhere on your paper. All right, so basically that means we're set up as x, x, and 2x, basing that on the stoichiometry of the balanced equation. So now they want us to calculate in moles per liter, the real x. All right, so what do we have here? Well, what is molarity? Molarity is moles per liter. And we have grams, so we have 1.72 times 10 to the minus 6 grams. So if we divide that by the molar mass, then we will come out with that divided by the volume in liters of a tenth of a liter. And we'll end up with the actual molarity of this situation, which is the solubility in moles per liter of the copper 2 hydroxide. So get your handy-dandy periodic table, and let's get this copper 2 hydroxide. Let's do the hydroxide first. Oxygen is 16, hydrogen is 1.01. That's a whopping 17.01, but do that twice. 17.01, but there are 2 of them. Plus, our copper is 63.55. And we come out with 97.57. You know what? That's often worth a point. So even if you don't know what you're doing or you get lost, make sure you calculate the molar mass and always calculate the number of moles of something, anything, so that you can get some points out of it. So here we have 1.72 second EE minus 2, minus 6. Yep, minus 6. Okay, divided by the molar mass I just calculated. I'm going to go ahead and get that numerator and then divide by 0.1, which is the same thing as multiplying by 10. And we come out with 1.76, or 2 sig figs good? Yeah, 2 sig figs are good. 1.76 times 10 to the minus 7 molarity. 1.76 times 10 to the minus 7 molar, or mole per liter. Or you could have just put it in square brackets. They all mean the same thing. So let's talk about points so far before I leave the screen, because we've racked some up already. Get a point for this equation. Balanced, make sure it's balanced, must have charges, must have balanced. If you're missing any of that, you don't get that point. And then a point, not for the, a point for this, and a point for this, for being able to calculate moles. Next, they want us to let the problem lead you. They want us to use some of the things that we have figured out, because we now know what x is, right? Because now we know that x, the real x, is 1.76 times 10 to the minus 7, 1.76 times 10 to the minus 7. And they want us to calculate the value of the solubility product, so won't that be 2 times 1.76 times 10 to the minus 7 for that amount? So It's always wise, even though they haven't asked you to do it, to write the expression. Yep, it's often worth a point. So from my balanced equation, there's my expression, and now that means that's x times 2x, looking back up at the top. Don't forget to square the 2x, because that hydroxide concentration is squared. So that is equal to 4x cubed. And KSP, the numerical calculation of it, is to now just plug and chug that. And you didn't need the 4x cubed part. That's just me kind of showing you that relationship because you ain't seen the last of it. So 1.76 times 10 to the minus 7. 2 times 1.76 times 10 to the minus 7, quantity squared, equals. Okay, so let's take this times 2, get that, square it, and multiply it by the 1.76 times 10 to the minus 7 again. And voila, we come out with 2.19 times 10 to the minus 20. And as always, if you took numbers out of the calculator, you're going to get a different answer than me. You should leave all the numbers in the calculator. But we do have a little bit of wiggle room there. So if you've got 2.18 or 2.20, we're good. We're good. Matter of fact, let's see, how many sig figs should I have on this? I probably should only have, well, no, 3's good. 3's what they've been giving us all along. All right, so a point for this and a point for this relationship. Whether you did it in X's, like I did up top, or whether you did it on your paper there, is fine. But you can't just go from writing the KSP to just whammo, a number appears out of nowhere. You're not going to get points for that. You're just shooting yourself in the foot when you do that. So far, we've done really well on this. 1, 2, 3, 4, 5 points already. So you're halfway there. At this point, when you feel like something's kind of rocking and rolling, and you're going, yes, cha-ching, cha-ching, cha-ching with the points, keep an eye on the clock on the real exam. You don't want the next part, which is only going to be worth the same number of points, to take you 2 or 3 times longer. So just be mindful of the fact that you're under a time crunch situation here. All right, so now the value of the solubility product of a different critter, zinc hydroxide, is 7.7 times 10 to the minus 17, danged insoluble, at 25 degrees Celsius. So calculate the solubility in moles per liter of zinc hydroxide at 25 degrees Celsius in a solution with a pH of 9.35. Okay, this is a hydroxide. That's a base. You know that from first year chemistry. pHs are about acids, but pH plus something called POH is equal to 14. We'll have a whole big giant unit on that, about how all the theory runs behind that. For now, just deal with the fact that if they tell you the pH is 9.35, you really need the POH because it's OH that's in this critter. And so that means that 14 minus 9.35 equals the POH, which was equal to 4.65. Did that in my head. Make sure I'm right. Therefore, if you want to undo the P part, the P part stands for the negative logarithm of. That means you take the base 10, because logs are base 10, and you put the minus sign on the POH, and that is the concentration of the OH minus ion. So to get that, I'm going to clear my screen because it's a mess. To get that 10 to the business on there, just go second log. See, 10 to the x right there. So second log gives me that 10 to the minus, don't use the minus sign, use the negation sign, 4.65. So I now know what 2x is in this case. So 2.24 times 10 to the minus 5 is the hydroxide ion concentration. So I want to solve for the zinc. Is that right? And calculate the solubility in moles per... Oh, I don't want to solve for the zinc. I just want to solve for X because they want the molar solubility. So I'm looking for X. What is X? All right, so I can now say, well, the relationship is that my KSP is equal to the zinc ion, which there's one of those, and the hydroxides, of which there are 2, so don't forget to square that. because I really need to be thinking about this equation. They didn't ask me to write it. They're just assuming that I know enough at this point that I can do it without it. But if you need to see it, write it down. ZnOH twice solid in equilibrium with its two ions. Zn2 plus 2 OH minuses. So that's X, that's 2X, and that's X. So that's where I'm getting all this. Okay, so now, if I solve for the zinc ion, isn't that the same thing as solving for the solubility? Because hopefully by now, after a few problems, you're embracing the fact that that's just X. So this is equal to the number they gave us, 7.7 times 10 to the minus 17. Therefore, X is equal to the concentration of zinc ion is equal to the molar solubility, BIL. Easy for me to spell, huh? There, molar solubility is equal to the KSP divided by the concentration of the hydroxide ion quantity squared, which is equal to, now do the math, 7.7 times 10 to the minus 17 divided by 2.24 times 10 to the minus 5. Don't forget to square it. Therefore, molar solubility equals, all right, so I've got that number sitting in my calculator. Let's just go ahead and square it. Take its reciprocal and multiply it by 7.7 second EE minus 17. So I come out with 1.5, 2 sig figs? Yes, why 2 sig figs? Another discussion. 1.5, trust me for the moment, times 10 to the minus 7 molar. Or put it in brackets, or use moles per liter, but don't leave it naked. A solubility is not naked. A K value is naked, and you should always celebrate its nakedness. But solubility is in moles per liter. All right, let's talk sig figs. You may not know this yet. You may not have even been taught this in first year. And there are even grown-ups that will argue with me over this. But I promise you, I'm not lying to you when I tell you that on a logarithmic scale, Richter comes to mind, pH comes to mind, decibels, logarithmic scale. The only part of that number, 9.35, that is significant is the part that comes after the placeholder 9. So the 0.35 are the only two digits there that are significant, and that locked me into 2 sig figs. If you put 3 sig figs, you're still going to get credit, because that's within the 1 forgiveness. If you put 1 sig fig, not so much. But well, maybe you would actually. 1 sig fig might accidentally get you credit in this case. But 2 sig figs is what I need. So 1.5 times 10 to the minus 7 molar. All right. And then finally, let's finish this little devil off. At 25 degrees Celsius, 50 milliliters of 0.1 molar zinc nitrate is mixed with 50 milliliters of 3 molar sodium hydroxide. Well, I can just eyeball that and go, 0.1, 0.3, that is not a 1 to 2 ratio, is it? That's a 1 to 3 ratio. Somebody's a limiting reactant. Somebody's going to be in excess. Calculate the molar concentration of zinc ion in the resulting solution once equilibrium has been established. Okay, let's talk. Think about this like you would as a Chem 1 student. I got zinc nitrate, and it's being mixed with NaOH. So now let's think about it as an AP chemistry student, net ionically. Nitrates are soluble. 1A metals are soluble when everybody's in solution. So net ionically, I have the zinc ion reacting with the hydroxide ion, and that's going to make ZnOH solid. Remember, it has an itty-bitty KSP, so it's going to make a bunch of solid. So you need to do the stoichiometry and push this all the way to how much solid you made. Then we can come back and use the equilibrium concept with the KSP value to wiggle our way into calculating that zinc concentration that they really want. Zinc ion concentration, she should say. Okay. You know I'm a fan of millimoles. I'm hoping that I'm kind of, winning you over. I can look at this and say 50 milliliters times 0.1 molar is 50 times 0.1, which is 5 millimoles. because molarity times liters is moles. So milliliters times molarity is millimoles. So again, 50 times 0.1 is 5. So 5 millimoles of the zinc 2 ion is present, mixed with 50 milliliters of 0.3. Well, that's going to be 3 times as much, so isn't that 15? So, and that needs a 2 there, sorry. So I have a 1 to 2 to 1 ratio here. This is 15 millimoles. Again, 0.3 times 50, right? I'm going to have 15 millimoles. All right, so now, what's the scoop? Well, somebody's limiting. Who's limiting? Well, if you used up all 5 millimoles of your zinc, you would need only 10 millimoles to react. Therefore, 5, that's not very good, therefore, is it? Therefore, 5 millimoles excess. That's what's going to be floating in the solution. Excess. And then, just for fun, I would make 5 millimoles of solid as well. Okay, so it's that excess that becomes important, and that excess is my OH minus ion as well. So now I can come to my KSP. Say KSP is equal to a number, 7.7 times 10 to the minus 17 still, and it's equal to a relationship of the zinc ion, which is what I seek, times the hydroxide minus ion, which I now know I have way more excess in that 5 millimoles than I have in that 10 to the minus 17 calculation. So this is one of those neglect X moments. I really technically should add the amount of hydroxide I would have, but it's so dang small that by the time I apply sig fig rules, I'm adding essentially 0. Because if you look back up here, what was X? 1.5 times 10 to the minus 7? That's 0.6 zeros and 1 5? Yeah, well, 0.005 plus all of that mess is going to round to 0.005 moles. All right, so I know that is X, and that is 2X quantity squared. So X is what I seek. That's my zinc ion concentration. And I know what the concentration of the hydroxide is. Don't worry about the 2X. You know flat out what it is. It is 5 millimoles of excess divided by how much total volume? 1550? Yep, 100 mils. This is why I'm a fan of millimoles. See, that cancels out nicely to moles per liter. So that quantity, don't forget to square it. So now just solve for X. X is going to equal the 7.7 times 10 to the minus 17 divided by, what's, 5 divided by 100, 0.05. Quantity squared equals 1.5 times 10 to the negative 14. I have twice that much, 3.1 times 10 to the minus 14. How come? Did I not square it? I didn't square it. That's how come. Duh. Forgive me. Let's try that again. There we go. That's what I had originally. 3.1 times 10 to the minus 14. Go figure. 3.1 times 10 to the minus 14. Mole per liter. Molar. All right. So, what's the twist on this one? That was a lot of work for 2 points at the end. So this is what I meant earlier by saying keep an eye on your time. As you work through any of the problems from now on, because you're getting really good at the equilibrium thing by now, if you're still listening to me at all, then you should be able to set a timer and work your way through an equilibrium problem in less than 15 minutes. Ideally, you're like an athlete in conditioning. By May, I'd like you to be able to work it in 10. And even have a little bit of time to go back and check your units and make sure you don't drop molarities and things like that you need. All right, so let's talk about the scoring on these last couple of bits. Up here, this molarity, getting that right there was worth a point. Being able to get that concentration of the hydroxide ion. And then getting the final answer was worth a point. And then in this piece, there was a point for all this substitution. And again, your work never has to look like my work, but you got to get the big idea in there. And the big idea was getting that moles of excess over total volume to calculate molarity of the hydroxide that is oh so abundant in this container, whatever the container may be. And then a point for the final answer. So 1, 2, 3, 4 points for that part, and you'd already racked up 5 points in the beginning. And remember, anytime you're getting 5 or more on an equilibrium problem, you are doing magnifico. All right, so shall we move on to the 2000s? Let's think right there, I think is where I want to go. Let's look at what they asked in 2004. So you kind of get the idea, and I've said this before, that about every 5 or so years, there's been a KSP. They have kind of shortened that from time to time and done 2 in a row on occasion, but I will tell you that as of this recording today, which is December 8th, my mother's birthday, God rest her soul, 2010, the 2010 back in May, so you're going to be taking the 2011 exam if you're listening to this fresh, otherwise it's beyond that, but in 2010 they also asked a KSP problem. So I'm not expecting a free response. I'm expecting lots of multiple choice. So the techniques that we are mastering here and moving quickly with are going to help you in the multiple choice as well. You're going to get tested on this one way or the other. That's all there is to it. It's just, will it be free response or will it be multiple choice? If I was a betting woman, I'd say multiple choice. All right, silver chromate dissociates in water according to the equation below. Well, that was nice. There's X, there's 2X, and there's X. And you gave me a KSP value. Yippee skippy. Write the equilibrium constant expression for the dissolving. Well, alrighty then. KSP is equal to concentration of Ag plus, quantity squared, concentration of CrO4, don't forget the 2 minus, and I will take that point, cha-ching, and move on. Now, calculate the concentration in moles per liter of the silver ion. That should be a plus up there. Typo, sorry about that. In a saturated solution of Ag2CrO4 at 25 degrees Celsius. Well, they had you write the KSP so that you could now come along and think about this more abstractly, because they want just X, is what they really want. So, KSP, like we just said, equals Ag plus, and you do not have to write this again, I'm doing this for clarity, equals 2X. How come? Because they gave us a balanced equation, and that quantity is squared times X. Now that's, you haven't seen one look like that in a while, have ya? Usually the 2X is trailing as the anion. This time it's the cation. I like that little twist. So don't forget to square the 2 to get 4. Don't forget to square X to get X squared. Multiply it by another X and you get X cubed. So now your KSP also equals the number 2.6 times 10 to the minus 12 at the top of the page. Therefore, X equals the cube root of 2.2 times 10 to the minus 12 divided by 4 equals. Okay. I like the math key. I like item 4 for the cube root, but you can do this any way you want. There's at least 2 other correct ways to put that in your calculator. I'm just too lazy to punch all those buttons. So 2.2 second EE minus 12 divided by 4. All under the radical for a cube root gives me X, which is 8.2. Hang on a minute. Do I have something written wrong? Yes, I do. It's 2.6. Duh. I wrote it wrong here because I saw that 2x. I'm so sorry. Okay, so let's try it with a 6 here. And I bet we get the right answer. Yes, that's more what I like it. 8.7 times 10 to the minus 5 molar. But is that our answer? No. Why not? Because we need 2x. So therefore the concentration of Ag plus was equal to 2x, which is equal to twice that. 1.7 times 10 to the minus 4 molar, or moles per liter if you prefer, or put it in square brackets if you like that. Okay, before I leave this screen, let's talk points at this point. There's one. That's the pity point. And then a point for the stoic, getting the 2x and the x business. And if you went all the way to 4x cubed, that's okay. They know you know what you're doing, and they give you that point anyway. I just don't recommend it because you can confuse yourself, especially since you wouldn't have gotten that visual of saying, wait a minute, it's the silver ion that is the 2x. Lots of kids made that mistake. All right, so now they want us to calculate the maximum mass in grams of silver chromate that can dissolve in 100 mils of water. Every time you see a volume in one of these solubility kind of things or any solution chemistry, think of it in terms of liters, and it's going to make your math a little simpler later. So x is what they're asking. Calculate the maximum maximum mass. Can you tell I'm a little bit under the weather? I'm a little nasal today. I got a little bit of antihistamine going on. I think it's messing with my thought process. So maximum mass. You ever get that like antihistamine fog grogginess? I'm there, folks. I am there. All right, so they want mass in grams. I can get moles in liters really easy because that's what X is. It's the molar solubility. And we know that to be 8.7 times 10 to the minus 5 moles per liter. So if I had 1 liter, that's how many moles I'd have, multiplied by molar mass of silver chromate, and I'm finished. But I only have 1/10 of a liter. So we have, therefore, 8.7 times 10 to the minus 6, 1/10 of a mole. So that bumps me one more place value of 10 in the smaller direction. So dissolves. Ag2CrO4 dissolves. So therefore 8.7 times 10 to the minus 6 moles times the molar mass. Oh, good grief, Gertrude. Okay, clear this. Get your periodic table. What do we got here? We got 2 silvers. How much is silver? 107. 107.87 to be exact. There's 2 of them. Plus, chromium's a nice round 52 if memory serves. Yes, 52. Plus 4 oxygens, 32 apiece. Isn't that 16 apiece. Isn't that 64? I believe it is. Double check my math. 331.74 grams per mole. And that'll give me the maximum mass. Okay, so take that number times 8.7 second EE minus 6, and we get 0.00. Make sure you get all the zeros written down properly. That's my worst habit. I get that wrong a lot, as you've seen. Dissolve. Okay, so in there in the middle of all of this equilibrium, boom, a stoichiometry moment. So expect it. Expect stoichiometry woven into each and every problem every time you have a calculator in your hand. Also expect easy math and stoichiometry in the multiple choice. Now, a 0.1 mole sample of solid silver nitrate is added to a liter saturated solution of silver chromate, assuming no volume change. Does the concentration of the chromate ion increase, decrease, or remain the same? And justify your answer. All right. What do you figure? well, let's look back at our balanced equation. What's going to happen? What am I adding? Silver nitrate. Common ion effect. All right. Here is, way up here, my balanced equation. So if I come along and I add silver nitrate to this, I am adding this into the situation. So the shift is going to move away from the addition, so it's going to go back this way. And for every 2 of those silver ions that get added into the situation, shift this back, it's going to take a chromium kicking and screaming and dragging over the other side as well. So the concentration will decrease. Concentration of CrO4 minus ion decreases since adding additional Ag plus ion, well, that's redundant, I could just leave Ag plus, shifts the equilibrium to the left. Favors reactants if you prefer, according to our good buddy, we won't write that part, Le Chatelier principle. Be expected, even though you have a calculator in hand on occasion, more often than not, you're going to write a sentence or 2 in the free response. And when you look at old problems from like the 80s and up to mid to late 90s, that's not the case. But as of late, they've been putting more and more sentence writing into the free response. So just be ready for it. No nasty surprises, right? Lots of practice. In a saturated solution of silver phosphate, the concentration of silver ion is 5.3 times 10 to the minus 5. The equilibrium constant expression for the dissolving of Ag3PO4 solid in water is shown below. Write a balanced equation. Wow, this late in the problem you get a pity point. Ag3PO4, didn't have to figure that out. They told me. That's my solid. Do the stoic. 3, hence the 3 right there. Plus, they even gave me all the charges. Okay, this was a pity point. All right, so this would be X, this would be 3X, and this would be X. So if I find phosphate ion, I know molar solubility and vice versa. Calculate the value of the KSP for this. All right, so they gave me what the Ag was. So Ag concentration, the silver ion concentration, is equal to 5.3 times 10 to the minus 5 is equal to 3x. So therefore, x is equal to the phosphate ion concentration, which is equal to 5.3 times 10 to the minus 5 divided by 3. What do you want to call that? 8? Yeah, 1.8 times 10 to the minus 5. Therefore, I needed that. I needed that because I need to write what the KSP expression really is. KSP is equal to silver. They gave it to me, right? So this is, I'm just copying it back down so you can see it right here. It's back at the top of the page, which is equal to 5.3 times 10 to the minus 5 quantity cubed 1.8 times 10 to the minus 5. That's why I went in search of that. So therefore, KSP is equal to this times 5.3 second EE minus 5 quantity, math, 3 cubed. And I get an incredibly low value of 2.6 times 10 to the minus 18. So that was really a fairly straightforward and basic piece. This is why you never give up on an AP problem. I think this was actually easier since they gave you all of this right here than the piece above. I haven't talked any points since part B. So I'll do that. I'll just finish this off because we're almost done. And I'll come back and get all the points for you. A 1 liter sample of this saturated silver phosphate solution is allowed to evaporate at 25 degrees Celsius to a final volume of 500 milliliters. So what? This is volume independent. What is the silver ion concentration of the solution? Well, it doesn't matter how much of the solution you have. If it's saturated, meaning there's some solid present, you're in the land of equilibrium, and you're in the land of KSP, and you're in the land of these molarities, whether you want to be there or not. So it doesn't change a dang thing, the fact that we let some of it evaporate. The Ag plus ion is still what you just calculated, 5.3 times 10 to the minus 5. Or actually, better yet, isn't it what they told you? Yes, it's what they told you. It's okay to also not give the value, but just say it was unchanged, or it did not change, or it's the same as. You know, it's the English language. You've got lots of different ways you can say it. Since the concentration of that silver ion in a saturated, that's the key word. This doesn't work just any old where. This is in a saturated solution. Is independent of the volume. And there you have it. Let's talk points. Don't let me make you dizzy. All right, I left off back. Let's recap from the beginning. How about that? Point for being able to write the KSP expression. I lovingly call it the pity point. Nothing wrong with the pity point. Take the pity point and run with it. And then a point for understanding the stoich, a point for actually using it and calculating the silver ion concentration. Then on part C, we get a point for calculating the molar mass, for the crying out loud. You could almost hit half of the mean on this one out of pity points. That's another pity point. So when all else fails, make sure you calculate molar mass as a number of moles. Even if you can't work much of the problem, at least try to get a point or two and don't zero it out. Zeros are just sad. And they do happen a lot. Then, 1 point for this. 1 point for using Le Chatelier's principle. Go figure, you'd have to use that in an equilibrium problem. And then another point for a balanced equation. Then a point for getting that 1.8 times 10 to the minus 5. Realizing that stoich. And then a point for using it to get the KSP, which I did not box. Shame on me. Oh, and that should have been a molar. The only thing that saves me from losing a unit point is that right there means molar too, so I'm okay. Sloppy, but okay. And then a point with the explanation on this. You can't just say the same. Must explain yourself. All right, we have one more. That's it. This will be number 6 in the lineup, and you probably worked some in class as well, and it's time. It's time for you to master this. Now, of course, you are a good student, and of course, you want to make me happy. So, of course, you have already worked this problem before you sit here with me and work it through again with me. Now you're just interested in seeing how you did. All right, several reactions are carried out using AgBr, a cream-colored silver salt. Cream color is going to become important later, or they wouldn't have told me. For which the value of the solubility product constant, KSP, is. They gave me the KSP, guess what? I'm going to have to write the expression, maybe even a balanced equation. So, before I even go too far, take a moment and do this. Because you're going to need it. So you might as well get that visual on your paper. I will also tell you that this was a 10-point question, and the mean was 3.66. Ouch. All right. KSP equals concentration of silver, concentration of bromide. Parentheses were not accepted. So I know you think it's picky sometimes, but these square brackets really do have meaning. So a point for that. This piece was also worth a point. Now they want me to calculate the value of silver concentration, silver ion concentration in 50 mils of a saturated solution. Well, don't let the 50 mils throw you off, right? Concentration's concentrations. What square brackets mean? So KSP is equal to x squared, since this is a one-to-one situation. Look back up at your balanced equation. See? X, X, X. And it's equal to 5.0 times 10 to the minus 13. Therefore, X is equal to the silver ion concentration that I seek is equal to the square root of 5.0 times 10 to the minus 13. Therefore, the concentration of the silver ion is equal to second square root, to get my radical there, 5 second EE minus 13. 7.1, 2 sig figs. 7.1 times 10 to the minus 7. A 50 milliliter sample of distilled water is added to the solution described in Part B, which is in a beaker with some solid AgBr at the bottom. The solution is stirred and equilibrium is reestablished. Some solid AgBr remains in the beaker. Could it be important that there's solid AgBr? Could it be important that it's saturated? Because as long as it's saturated, then we're still in equilibrium. And we still have the same concentration. So the solution is stirred, equilibrium is reestablished, some solid, is the value of the silver ion greater than, less than, or equal to the value calculated in Part B. Okay, folks, here's the point. Didn't matter that you only had 50 milliliters of solution. Could have had 3 liters of solution. Could have had 35 gallons of solution. As long as it is saturated and it has some solid present and it has established equilibrium, you still have moles per liter of 7.1 times 10 to the minus 7 in the case of the silver, or the bromide, since they're the same. So, is it greater than, less than, or equal to? Equal to the same value as long as the solution remains saturated, or as long as solid is present. You got to get that piece in there. You got to say that solid thing that they told you twice is an important piece of evidence in your conclusion. All right, I call that a super easy question. I got to admit, my students would have called that a trick. They'd say, that's a trick question. And why? Because it's too easy for you? It's easy. If it's saturated, then your concentration didn't change. Now, no, if they don't mention the solid on the bottom, all bets are off. Calculate the minimum volume of distilled water in liters necessary to completely dissolve a 5-gram sample. What is this KSP value? Uber small, 10 to the minus 13. This is going to take a lot of water for 5 whole grams to dissolve. And they were kind enough to give me a molar mass. That's good news and bad news. Good news, yay, I don't have to calculate it. Bad news, boo, I don't get a point for doing something that easy. All right, so the concentration of the Ag plus is equal to the molar solubility, right, is equal to X. That's the concept you're going to get started with. And that's equal to 5.0 grams divided by that molar mass to get moles. Are we in agreement that it's an expression for moles of the silver bromide over X liters? That's my relationship. So I'm using the fact that I know the molarity, which is 7.1 times 10 to the minus 7. Let the problem lead you. You calculated the molarity earlier, right? Right there. So now come and use it and solve for X liters. So X is equal to my 5.0 grams divided by 188 grams per mole. That's code for moles right there. All over 7.1 times 10 to the minus 7 moles per liter. Notice how cancel, 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 cancel. A 1 over liter is liters. That's a very good thing if I'm looking for liters in volume. Volume in liters. All right, so do it. 5 divided by 188. Let me get that numerator and divide it by, that's value that's sitting right there, and enter. I get 37,612. That's calculator vomit. You need how many sig figs? 2. 5.0 gram sample. 38,000 liters. That deserves an oh my in honor of Dorothy in The Wizard of Oz. Okay, so let's talk points up to here. 1 point for that pity point up there at the beginning. 1 point for this. 1 point with the explanation here. The easiest point. Is the solution saturated? Solution saturated. Concentration stays the same. 1 point for being able to calculate moles. And then 1 point for the final answer. A student mixes 10 mils. Okay, mixes. Mixes always gets you in trouble. Either a precipitate's going to happen or not. Who precipitates first? Or who's the limiting reactant? Are the three things that are coming at you when you have the word mixing in a problem. So a solution antihistamine. Okay, a student mixes 10 milliliters of 1.5 times 10 to the minus 4 molar silver nitrate with 2 milliliters, so that's a total of 12 milliliters. I always like to write that down so I don't have to think about it again. Of 5.4 times 10 to the minus molar bromide. Okay, are we in agreement? Spectator, spectator? If we're not, then you need to listen to the recordings on polyatomic ions. Not polyatomic ions, I'm looking at one. Net ionic equations, thank you. Okay, get those matched up. What will the student observe? Justify your answer with calculations. Well, you're either going to make a precipitate or you're not. So what would the student observe is just a chicken you-know-what way of asking if a precipitate is going to form or not. So let's solve for each ion's final concentration, get a QSP, compare it to a KSP, and the student will either observe solid junk occurring in the test tube or nothing, which is not expected because that's kind of like boring. So Ag plus. That would be my 10 milliliters times its concentration to get millimoles. So my liters cancel and I get millimoles for that, divided by the total volume of 12 milliliters. So that really cancels all that out and I just get moles per liter, really. It cleans up nicely as well. And that is 10 times 1.5 times 10 to the minus 4 divided by 12. Okay, so let me clear all this mess out. I should have just done that part in my head. Sorry, too late now. Divided by 12. 1.25, let's call that 1.3, times 10 to the minus 4. Concentration of Br minus is equal to 2 milliliters times 5.0 times 10 to the minus 4. You do recognize this hopefully as M1V1 equals M2V2, where if I'm solving for concentration, I'm solving for M2. Milliliters cancel. I get a molarity. So 2 times 5 times 10 to the minus 4 is 10 times 10 to the minus 4, which is 1 times 10 to the minus 3. Did my head that time. Divided by 12. Watch it be wrong. But it's not. 8.3 times 10 to the minus 5. She wins one every once in a while. Therefore, I'm going to need more room. QSP is equal to the product of these two things. I don't want that one. I went too far. That one. Times that one. Now, I'm using more digits because I'm lazy, but I still come out with 1.04, call it 1.0, times 10 to the minus 8, So now I've got to compare QSP to KSP. So one more time, why are we doing this? Student mixes junk in a test tube. Trouble? It's always trouble. So what does the student observe? Well, you're in a solubility problem. Well, you've done all this KSP stuff. You're going to either make a precipitate or you're not. And then if it's the one they told you was all pretty and cream-colored, you can even add that in. If you make AGBR, a cream-colored precipitate's going to form. So compare Q to K. I like the whole alphabetical thing. K comes before Q in the alphabet. They're both SPs, so it's a valid comparison. We know that QSP is 1.0 times 10 to the minus 8. And you do not have to write this way. I do this for you so you can see it. You can line them up and you can see it better, and that helps your brain sort it better. And the KSP was way back up at the top of the page. 5 times 10 to the minus 13. 5 times 10 to the minus 13 is way smaller. Okay, so the arrow points to the small one. The arrow also tells you which direction that this reaction is going. So if you look at the balanced reaction, it's going this way. Right? Not very pretty. It's going that way. So it's going to make solid. Therefore, a precipitate of AGBR, you can put the cream colored in there if you want, forms. Points, points, points. This is worth 3. A point for the pair of those. However you did it. You didn't have to sit and solve for them separately the way I did. That's just my technique. A point for calculating QSP and comparing it. You had to do both things. Calculating QSP and comparison. Making one. And then a point for drawing the right conclusion from the comparison that you made. So you could make a comparison, still get the point, but then lose it because you concluded incorrectly because you were a doofus and you had your arrow backward or something. I see it happen a lot. Alright, we're in the home stretch, folks. The color of another salt of silver, AgI, is yellow. So cream-colored, AgBr. AgI is yellow. A student adds a solution of NaI to a test tube containing a small amount of the AgBr. Okay, so AgBr is already solid in there. Now we're going to add NaI. You know, the Na is just a spectator. So you're adding I minus. This is a single replacement, isn't it? If anything happens at all, I will bump bromide, iodide will bump bromide out of there. Only way we'll know is if there's a color change. After stirring the contents of the test tube, the student observes the solid test tube changes color from cream to yellow, and yellow was AgI. Write the chemical equation for the reaction that occurred. You can do it molecular, or you can do it net ionic. So you can either do AgBr solid plus I minus, which is the way I'm going to do it, which is net ionic, is going to now make me the yellow AgI solid plus Br minus. Okay, so that was easy. Don't try to make that hard. That was just easy greasy Chem 1 stuff. Now, here comes the tricky bit. Which salt has the greater value of KSP? AgBr or AgI? And justify your answer. Well, there's 2 ways to do this. There's a math way and there's a word way. The math way is probably simpler. So we'll do it first, and then we'll come back and do the word way. Because it doesn't matter which one you do. It matters how you think this through. Doesn't this look a little bit like adding a couple of equations together that were both KSP type equations? Yes, it does. Yes, it does. The KEQ for the displacement reaction, you see it as a single displacement? One single thing bumps somebody out, takes its place, leaving a new single over here. When I taught it to Chem 1 kids, I always said that was like somebody stealing your girlfriend or your boyfriend. Now, the AgBr would be written in the forward direction. But doesn't this look like AgI is written in the backward direction? So when you reverse a KSP reaction, which always starts solid, yields ions in equilibrium with ion and ion and ion, however many there are, then you flip the value of the KSP, so that means it's really, I'm multiplying the KSP of AGBR times 1 over the KSP of AGI. I'm just combining it into one final mathematical expression. That's what KEQ would really equal. So since yellow AGI forms, KEQ is greater than 1. Therefore, the KSP of AGBR is greater than the KSP of AGI. So mathematically, there's your explanation. Now, if you don't like the mathematics, then let's do it more conceptually. This reaction happened. How do we know? Because yellow showed up instead of cream. Alright, so AGBR still has a greater value. Now let's say that's not your first thought. Just leave yourself some room and think this through. The precipitate will consist of the less soluble salt. Duh. When both I minus and Br minus are present for silver to lock onto. Since the color of the precipitate in the test tube turns yellow, it must be AGI solid that precipitates. That's not very pretty. Meaning it has the lower KSP value and gets reached first. Alright, so that's what leads me to the fact that AGBR, to answer the question up front, has a greater KSP value. Now I'm going to say it again. Therefore, the KSP of AGBR, to finish off my sentence, must be greater than the KSP for AGI. Okay, I'll leave that there for a second. So math may be your friend, words may be your friend, but either way, if you mix another ion in there, and that ion is the one that then changes the color of the precipitate. So that's why they had to tell you cream color and yellow. The yellow forms, that means that critter has the smaller KSP because it got to the solid state faster. And that means the other one that has the greater value. So it was a little bit of a backward question. So that one you had to think about really hard. And you know what? It was worth 1 point. So that was a lot of work for 1 point. So, you've heard me say before, sometimes you got to know when to fish or cut bait. That might have been a cut bait. You look at the clock. Is question 1 if you chose to start with equilibrium. If you spent your allotted time on it, move on. You can come back to it later if you get stumped on something else. But you have got to watch the clock. You will have 50 minutes with your precious calculator to work 3 problems. Don't think problem means I don't ever have to write a sentence, because you're going to be writing some. So I implore you to practice, 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 and keep practicing all the way up until the AP exam. I hope you have a great rest of your day, and I hope I can clear up my antihistamine fog and feel better soon. So wash your hands often so you don't catch any colds. Thanks so much.